We will resume the chapter 5 today. So in this chapter 5, the topics that we have been learning are scheduling. So what is a scheduling? Basically that whenever we have multiple process, the operating system has to decide how to handle multiple process so that everyone gets part of the resources, and also overall performance is optimized, and at the same time the throughput, that the number of the number of process that being handled at a certain amount of time is actually increased. So basically we want to maximize the throughput, okay, we want to minimize the response time, and we want to make it fair. That means everyone should actually get the CPU. There are different scheduling algorithms, but our main focus is this four: first come first serve, shortest job next, shortest remaining time, round robin. Okay, so these four is our main concern. Last class we have talked about first come first serve. In the first come first serve, what we have seen, that the jobs come as their own, and after that the job that actually comes first get the CPU first. Okay, and we have calculated the average waiting time and average completion time. Okay, so these are the two terms that we have calculated. Um, and now one thing that we also have done, that we have seen that if depending on the order, that means if the shortest job arrives first and the large job arrives later, okay, depending on the order of the jobs or the process, it takes actually a different amount of average waiting time and average completion time. So we have calculated for the same CPU, the same process, we have actually done two calculation, and in those calculation we have seen if the shortest job arrive first, it takes low amount of completion time and waiting time, but if a large job arrives first, it takes a long amount of time. Then I have talked about what is a preemptive process, what is a non-preemptive process. So the idea behind the preemptive and non-preemptive is this, that once the CPU has been allocated to a process, the process keeps the CPU until it releases the CPU either by terminating or by switching to the waiting state. So that means if you allow someone to have the CPU, he will not give it back unless it's being terminated for some reason, maybe it's over or there's a violation, or maybe it's waiting to switching to waiting state for some IO or interrupt. And the scheduling method is used by the Microsoft Windows 3.1 and the Apple Macintosh operating system. And preemptive is the modern one. In this type of scheduling, the tasks are usually assigned with priorities. So at times, if necessary to run a certain task that has a higher priority before another task, we actually use this type of scheduling. One example that we already have studied is called interrupt. In that interrupt, we have seen that even though there is a process going on, there might be a higher priority process. And I don't think if you remember that there was a different ways to handle multiple interrupt. One was priority based. So that means if one interrupt is going on and then there's another interrupt comes, in that case we use this method. Now, the different scheduling algorithms that we have, the non-preemptive, that means the CPU will not be allocated, is first come, first serve, and shortest job next, okay? And in the preemptive case, that means CPU will be taken, allocated for a certain amount of time, and it can be taken back. We have priority scheduling, we have shortest remaining time, we have round robin. So let me go back to the discussion again. Let me close this slide. So this was the example I was talking about, the first come first serve. Initially, when the process one with the 24-second burst time came first, uh, it took overall 17 second and 27 second in average waiting time and average completion time. But when we changed the order, P2 and P3 came first, it dropped to only 3 second and 13 second. So our what we wanted to do, how we can actually improve this, okay, how we can actually improve the performance. So for that, there came the round robin scheduling. In the round robin, what we do, we basically allocate the CPU for a certain amount of time, and after this certain amount of time, we actually take back the CPU. So whenever we are actually using this algorithm, what we are doing, that CPU, you can, each process, P1, P2, P3, they will get a CPU for a certain amount of time. And by that time, if it's not done, okay, he will have to give it back. So let's talk theory later. Let's just see an example. Here we have this three process, P1, P2, P3. So in this round robin, okay, we have one new concept, that is we call time quantum. What does time quantum mean? Time quantum means that each process in the CPU will get a CPU for 4 seconds. Each process will get for 4 seconds, and after 4 seconds, you have to actually leave. And if you are not done, okay, you have to again join. It's basically like you are in the line. So every time you want to get a service, you have 4 minutes. If you can finish within that 4 minutes, then it's done. If you're not, you have to go back and again join at the end of the line. Let's assume you want to do some photocopy from a library, and you're allocated only 4 minutes of computer time. If within 4 minutes you can finish your task, then it's good. If not, you have to again leave the computer for the next person. Now, here's a Gantt chart of how it works. If you see that P1, P2, P3, okay, so P1 is started with first, P1 started with 0, and from 0 we have up to 4 seconds, and from P2 we have 4 to 7 seconds, and so on. Now, the process P1 and process P2, okay, the idea is very simple, that P1 have 24 seconds, it got the CPU, it used for 4 seconds, as the time quantum is 4 seconds. So he worked for 4 seconds, and after that, okay, P2 came. So as you can see, P2 only needs for 3 seconds. Okay, so he took the CPU at 4th second, and 4 plus 3 at the 7th second, he will actually leave the CPU because he is done. And at the 7th second, again, P3 took the CPU, okay, and after 3 seconds, P3 is also done. So at the 10th second, P3 will leave the CPU. So P2 and P3, they are done. So P1, he will again take the CPU at 10th second, and after 4 seconds of work, he will again leave the CPU. As there are no other process waiting, P2 and P3 are already done. So P1 will get the CPU again, P1 will get the CPU again, and so on. So basic idea is this one, that if you have multiple process, you will allocate each process the CPU for a certain amount of time. And this is the concept behind round robin. So each one actually getting the CPU for a certain amount of time. This is the basic idea, that given you have multiple processes, what we do, we first fix our time quanta, that is 4, that for this amount of time, everyone can use the CPUs. After that, whether you are done or not, you have to leave the CPU for the next process. Okay, and if you are done, you will leave, just like the way P2 and P3 are done, so they have left. Okay, but if you're not done, you have to join the line again. You see, so P1 joining the line multiple times. Okay, he's leaving the line and joining at the same time. So if there was another example, it will be actually much more easier to understand. So let's look at this one. So here what we did for the first example, we calculate the waiting time. Now the concept here is a little bit different of the waiting time, because previously, whenever we calculated the waiting time, the process actually had to wait only once. But now the process will get the CPU, then again you have to wait a little bit, and then again you have to wait a little bit. So it actually becomes complicated if you want to calculate the actual waiting time. So for now, for simplicity, we actually only calculate the basic waiting time. Now, if you look closely, okay, if I want to calculate the waiting time for P1, okay, so P1 first started with 0. Okay, okay, this is the same example. Let me get another one. In that way, we can solve 2.
Sir,
1 second. In this example, okay, we have actually, you see, if you look closely, we have how many process we have? We have 1, 2, 3, 4, 5, 6. 6 process. First difference, you will see that they have now different arrival time, and that's what actually makes it a little bit complicated, because in the previous example that we have done so far, we have assumed that everyone have the same arrival time. All the friends or all the process arrived at the same time. They're just waiting in a different serial. But now you see, in different amount of time, the process will arrive at a different moment. So the first process arrived at 0 second, second process arrived at 1 second, third process arrived at 2 second, and so on. So this is the first change. Okay, and this is actually the real case scenario, because in the real life scenario, okay, the processes will not arrive at the same time, because different amount of tasks are actually being done in different amount of time. So this is a real scenario. Now, this picture actually looks a little bit complicated, but let me explain part by part. So first of all, this is our question. These are the processes we have, and these are the arrival time. Okay, the first, as I said, the first process arrived at 0 second, second one at first second, second, and so on. Okay, TQ is basically the amount of time quanta. So each process will be given 2 seconds to finish its task. If you are done within the 2 seconds, good. If you are not done, okay, go back. So this is the second case. And BT, basically the burst time, the amount of time needed for each process. So each process will need, the first process will need 4 seconds, second one will need 5 seconds, and so on. So this is our question. Okay, now let's start. Okay, so here we will use a queue, or Gantt chart, or whatever you said. So basically, let's think about the system. The computer started, and the 0th second, there is a person P1. Okay, so he is waiting for the service. So obviously he will get the service, right? So at beginning, this queue starts with P1. Okay, this will feels a little bit complicated at the first time, so just hang on. Second time I will explain it again, and you will see that this is not a very simple topic. So let's start with P1. At the 0th second, that means when it started, there's only one process, that is P1. So P1 will get the CPU. So in the queue, we have first P1. This is P1. Okay. So after P1 is done, remember when P1 is done, what is the time? The time is seconds, 2 seconds, right? And in that time, there is actually two process in the three process. So when P1 was working with the CPU, by that time in the first second, P2 arrived, and in the second, P3 arrived. So now, how many process I have in the CPU? I have in the queue, I have P1 who is currently executing or done executing for 2 seconds. I have P2 who is waiting in the line. I have P3. So this queue actually represents that, okay, that which process are coming. So what will happen? So P1 just finished. So P1 will be taken back and added at the end of the queue. I hope that all of you know how queue work. Okay, so queue done. Then P2 will get the CPU. So here, as you can see, P2 got the CPU. So for the next 2 seconds, the CPU operating system will not change anything. P2 will get the CPU, and from 2 seconds to 4 seconds, okay, the P2 will keep processing. Now, while the P2 is doing processing, if you look at the list, by that time, two other processes have arrived. So after P1, we have another process who arrived, P4, and we have another process which arrived, that is P5. So basically people are joining in the line. Okay, we can say this is the person 1, person 2, person 3, and after person 1 was done, okay, he joined at the end of the line, and between 2 seconds to 4 seconds, two other new people came, P4 and P5. They also joined in the line. Okay, so at the 4th second, okay, what happens? P2 is done, so he will join at the end of the line. So P2 has joined at the end of the line. Okay, now who is next? P3, right? So P3 will start working from 4th second to 6th second, and during this time, no other process will get the CPU. And when the 6th second is over, as you can see, there is another process, that is P6, that is end of the line. So P3 is over, and P3 will go back and join and end of the line. But if you look closely, the burst time for P2 is 2 seconds. So basically he doesn't need to join anymore. He will not join the line. I know I made it more complicated than it looks. Let me clear it up and again try one more time. At the beginning of the line, when there was no one, person P1, the person 1 came at the first beginning of the line, and as the line was empty, he started working with the CPU. He worked for the first 2 seconds. Now remember, there's two parts here. The first part is the queue, where we actually keep track that so far how many the queue where we keep track that which process will go after which process, just like a line in any place. Okay, And this one is the Gantt chart, where we calculate that when a process starts working and when a process finishes. Okay, so these are the two different tasks. This one to keep track that which process will come after which process, and this process is to keep track of the time. Now, okay, let me restart the meeting. We have only 30 seconds left.